We're looking at volume of revolution as an extension of volume of surface of revolution. And we're looking at talking about the method of Dis and method of washers. And the volume of surface of revolution, the previous video, we already covered the method of Dis, even though I didn't use that phrase. See, if we have a look at the diagram here, and this was treated in the previous video, and so if we look at, we've got a rotation around the y-axis of a function, and the function given there is rotated around, and as we vary along y, we get an infinitely thin disk at each place, and those disks are basically, as I said, cylinders. And the idea is to apply the idea of a limit of a sum there. Okay, and they're full surfaces, and the disks change their surface area. Okay, and we got the formulas you see below there in the previous video. So that's method of disks, as it's called at certain times. Now, regardless of whether we're rotating something around the x-axis or the y-axis, the function, the line of the function itself, has an unimpeded region below it, straight down to the relevant axis, depending on which axis it is. So it could be something like that if we're got an interval there and there, that region there. And if we rotate that about the x-axis, we'll get a solid, and we can use disks like that. This was all covered in the previous video, but what of washers? When I say washer, it's like a disk with a hole in the center, and you'll see washers used in a number of different things, with nuts and bolts, perhaps inside a faucet. But you can see that it's a disk with a hole inside. So what has this got to do with calculus? When we have an area or a region bounded by two functions, like we've seen before, we've calculated the area between these in previous mathematics. What about if we rotate that region around one of the axes? For example, this one around the x-axis, what would we get? And this is where the idea of the washer comes in, because we don't have a full solid of revolution. We do have a volume of revolution, but not a solid one, because there's a quote-unquote a hole in each of the washers, to use jargon that's not strictly mathematical. So this picture on your left here that I've taken from an AP Calculus website, the reference is given below, shows this idea. We have an axis, so-called typical washer, and you can see that as we have the two functions there, these ones are going to be rotated about the x-axis. So we have f of x and g of x. If it was vertical, we'd have f of y and g of y. But you can see there's a void in the middle, which varies according to the function or the difference between the two. And we have a typical washer would have cross-section like that, but it would have a void in the middle. And it would have a thickness, and the idea is to get infinitely many washers, infinitely thin, to get the exact volume of revolution. So that's where the idea of a washer comes in. An example might be something like this one here, where we've got two functions and a region, and if we rotate that about the x-axis there, we will get a washer situation there. And you can see that because the region varies in area as we go across it, elements of our interval, the effect of the void will change. Okay, and also the extremes of the region at the top and the bottom will as well. So, for example, on that one there. Okay, and it's not just around the x-axis, it can be around the y-axis as well, as we see further down here. This one here will be rotated around the y-axis, so we have two functions in terms of y, f of y and g of y, and likewise this will create a series of washes, as it were. So essentially, when we have the difference between disks and washes is essentially based on the difference between an area under a curve being rotated around an axis and the area or the region between two curves rotated around one of the axes. Okay, and basically this translates into formulas that we see here. So now we need to be careful. If g of x is greater than or equal to f of x over an interval. Okay, now some books will use f of x here and g of x there. Look, it doesn't matter, it's just notation. The important thing is we need to determine which is the greater function over the interval. Okay, and so if g of x is greater than or equal to f of x over the interval, we would use it that way. Otherwise, f and g would be swapped around. Okay, so just understand how it works. So you can see that it just builds on the idea we saw with volume of solid of revolution. So we have volume here is pi times the integral between a and b of gx all squared minus f of x all squared dx. And for situations around rotating a region around the y-axis, if g of y is larger than f of y across that interval for y, then we use the volume is pi outside the integral of a to b g of y all squared minus f of y all squared dy. Okay, let's have a look at an example which does both of these. I'll leave some of the working out of this example just to keep the video reasonably short. So determine the volume form when the area between the curves y equals x squared and 8 minus x squared is rotated firstly around the x-axis, then the y-axis. So you should be able to see the two graphs plotted there, x squared and 8 minus x squared. Now the points of intersection would be handy here. Okay, technology says they're negative 2, 4, 2, 4, but if you have to do it analytically, you set the two equations equal to each other, and x squared equals 8 minus x squared. Okay, yeah, yellow wasn't very appropriate then. It was a surprise to me too. I was expecting blue, but there's the blue. And if you need to do it manually, you can find the intercept there for each of the curves. For example, 0.8 for the green there. They're going to be handy bits of information. So the region we're rotating, if we're going around the x-axis first, will be this region here. Okay. So what does it look like if we rotate this thing? So what I've tried to do is have another look at this, yellow again. This volume there, you can see when it's rotated 180 degrees around, we can see that same region down there, and we can see the effects here. And basically you can see that the extremes there correspond to those points of intersection from earlier on. And likewise over here, you can see the effect. Here's a sort of a typical washer, so-called typical washer there and there. And you can see the variance as it would flow through there, and likewise that way there. Okay, so that's the typical washer there. So we're looking at the volume of revolution around the x-axis. So let's go ahead and do the calculus. So we're going to let, again, it's up to you whether you want to make f or g the higher function. Okay, I'm deliberately changing them around each video just so you see that it's just arbitrary. So the one that was higher up is x squared in the as far as the region goes, and let's make g of x equal x squared, and f of x lower down is 8 minus x squared. Oh, whoops, I just realized actually the other way around, the f of x is higher than g of x. See, it doesn't matter as long as it's set up correctly. Okay, so in this one, okay, so let's find that volume. And we've got in this one f of x squared minus g of x squared okay, so we'll get in and do that. Okay, remember the limits of integration. They're going to be 2 and negative 2 from before, okay? And so we would have this set up, and I'll go through quickly now because the integration part should be familiar to us. It's setting it up to the new part, which we get that. Take a factor of 16 out and integrate after we simplified the x to the power 4, and we apply the limits now. I get 512 pi on 3 units cubed. Now, as far as the around the other axis goes, around the y-axis, what it really means is it's not what I selected there. Yep, that's better. We're actually rotating. To rotate this around the y-axis, one way of visualizing that is if we just take, it's symmetrical, so it doesn't matter whether you take the left or the right or both sides, but it's like whipping this yellow region around here, around this y-axis. Okay, so we'll have that sort of shape there. So with a graphic helper, we've actually got the volume of a solid of revolution here. Okay, so it's a solid. So it wasn't a washer, it was a disc one. And so what we've got to be careful of is when we take the volume of that, and okay, remember we are going around the y-axis here, we've got to look at what it's bounded by. So in this interval here, at y equals 4, and we found that 4 value at the start of the video, when we looked at the points of intersection, it's bounded by a certain function there at the top, and it's bounded by a different function in the bottom half there. So you've got to be careful. So it's bounded by two different functions, which we've got to find. Okay, so the top one you can see is to do with this, but it's in terms of y, and the bottom part is in terms of this. So for the function, we have to treat these separately. For the function y equals x squared, or x squared equals y, we have that there. We could say x equals plus or minus the square root of y, but we've got to square it anyway. So we want y to go into the function. Okay, because remember the function has the squared application. For the other one, y equals 8 minus x squared equals 8 minus y, x equals plus or minus square root of 8 minus y. But again, we want the squared application, so it's just 8 minus y is what's going to go in there. So putting that in, we have y between 0 and 4 for y squared dy plus pi outside of 4 to 8, and we have 8 minus y dy. We integrate that, and I'll do that quickly. So we've got a third y cubed between 4 and 0, 0 and 4. It's 8x minus a half y squared between 4 and 8. And, whoops, not dy. Evaluating that now, we get 16 pi cubic units.